Hello and welcome. Today we're looking at acids and bases in organic chemistry, presented to you by Science Visualized. There are three definitions for acids and bases: Arrhenius, Bronsted, also called Bronsted, Lowry, and Lewis. Arrhenius acid contain or have hydrogen ions. Arrhenius bases contain or have hydroxide ions. So an example of Arrhenius acid is HCl, HBr, while Arrhenius base will be NaOH, KOH, and they all contain hydroxide ions, while the acid contains hydrogen ions. So the acid contains hydrogen ions, the hydroxide contains hydroxide ions. Bronsted acid, they are hydrogen ions or proton donors. So hydrogen ions is the same thing as proton. They donate hydrogen ions or protons. An example of that will be HCl, HBr, and they can all donate the hydrogen. That's a proton, the hydrogen ion. The Bronsted base accept hydrogen ions or protons. So an example of that will be OH minus from sodium hydroxide or potassium hydroxide. So they will accept hydrogen ions. The Lewis acid are electron pair acceptors. So they will accept electron pairs. Lewis acids are usually transition metal salts, like say tin tetrachloride. So transition metal salts. Group 3 compounds, like say boron trichloride. The carbon position of the carbonyl, if you have a carbonyl like that, that position there can accept electron pair. And then lastly, carbocations, that's positively charged carbon intermediates and protons. All those will accept electron pairs. The Lewis base donate electron pair. So example of that are compounds that contain oxygen. If you have, for example, water, you have two lone pair of electrons, so you can donate one of those pairs. Same thing with sulfur, carbonyls. That carbonyl has two electron pairs that can donate one pair. Compounds that contain nitrogen, like amines, so RNH2, that nitrogen has an electron pair. And lastly, negatively charged species. In summary, we say Arrhenius acids contain hydrogen ions, Arrhenius base contain hydroxide ions, Bronsted acid donate protons, Bronsted base accept protons, Lewis acid accept electron pair, Lewis base donate electron pair. Bronsted acid, also called Bronsted-Lowry acid, they are proton donors. So they donate protons. Remember, proton is H+. A Bronsted base accept hydrogen ions or protons, so they are proton acceptors. Example, here we have water reacting with HCl, hydrochloric acid, and that's giving H3O plus Cl minus. Look at what happened. We started with 2 hydrogen atoms on water, and now that increased to 3. So that means the number of hydrogens has increased. So from water to H3O plus, we added one more hydrogen ion. And because we added a hydrogen ion, then that means this water here accepted hydrogen ions, and because of that, it's a Bronsted base. Then if we look at this species here, HCl, it gives you Cl minus. So what happens is that you lost hydrogen ions. And because you lost hydrogen ions, that means it donated hydrogen ion. And because it donated hydrogen ion, it becomes a Bronsted acid. Bronsted base will accept hydrogen ions to give a conjugate acid. Bronsted acid will donate hydrogen ions to give a conjugate base. So in other words, a conjugate base comes from the Bronsted acid, while a conjugate acid comes from the Bronsted base. So here, Bronsted acid loses a proton to become a conjugate base, while a Bronsted base accepts a proton to become a conjugate acid. Now equilibrium constant, KEQ means equilibrium constant. Looking at this reaction where HA is a generic organic acid, that means it can donate H+. HA reaction with water ends up protonating water, so you get H3O plus, that's called hydronium ion, while the A becomes its conjugate base, which is A minus. We can then write the equilibrium constant for this reaction. The equilibrium constant always equals to the concentration of the product, and to show that its concentration we use square brackets to show that its concentration. So concentration of the product divided by the concentration of the reactant. We know there are two products, H3O plus and A minus. So we use the concentrations of those two. So concentration of H3O plus times the concentration of A minus divided by the concentration of the starting material HA and water. So that gives you the equilibrium constant. Now, since this reaction, everything is dissolved in water, that means there's a lot of water, then it's better to take water out of the equation by multiplying both sides by the concentration of water, and then here too. And when you do that, you end up now with water concentration times KEQ, which gives you a new constant called Ka. And that constant doesn't have water as part of the equation. So the KEQ times the concentration of water gives you Ka, which then has these three concentrations as part of the equation. So you have it here. Ka is called acidity constant. It's a very important constant in organic chemistry because we can use that to measure the strength of an acid. Strong acids, they have high Ka. Weak acid, on the other hand, will have low Ka. The reason for that is because Ka is directly proportional to H3O plus. But this H3O plus is really water plus H plus. So it's directly proportional to the concentration of hydrogen ions. And we know that the pH is equals to minus log of the concentration of hydrogen ions. So that means high concentration of hydrogen ions, which means high concentration of H3O plus, means you have high pH and therefore going to have high Ka. Strong acids have high pH and they have high Ka. Remember that pH equals to minus log of the concentration of hydrogen ions, and we know that hydrogen ions concentration is the same or proportional to H3O plus, because H3O really consists of water plus H plus. It's an inverse relationship. High pH means low concentration of hydrogen ions. Now we can use that with pKa. Remember the acidity constant. pKa equals to minus log of the acidity constant Ka. So that means low Ka means high pKa. Low Ka means weak acid, and that would mean you have high pKa. So the relationship between Ka and pKa is inverse, opposite. That means when Ka increases, pKa decreases. Therefore, high Ka means high concentration of hydrogen ions, which means a strong acid, but it also means low pKa. On the other hand, low Ka means low concentration of hydrogen ions, weak acid, and high pKa. Strong acids will donate hydrogen ions, that's proton, easily, and therefore they have high Ka and low pKa because the relationship between Ka and pKa is inverse. If Ka increases, pKa decreases. Weak acids do not give or lose their protons easily, and therefore they have low Ka and high pKa. Again, we see this summary here. Strong acids, high Ka, low pKa, and it has a weak conjugate base. A weak acid will have a strong conjugate base. Bronsted acids. Organic Bronsted acids. They contain the proton or hydrogen attached to oxygen, as in alcohols, or to nitrogen, as in amines. Or the H are on the carbon next to the carbonyl. We call that alpha position. So this position here is called alpha. You have the carbonyl carbon there, so that's a carbon double bond O, and then you have two alpha positions. The alpha hydrogens are acidic. You can donate them. So here we see some examples of Bronsted acids. Compounds that contains OH, as in water. Alcohol also has OH. Amines, they contain NH, or carbonyl compounds, alpha position. Organic Bronsted bases. They contain lone electron pairs or a negative charge. So for example, water has 2 electron pairs that can easily be donated. Alcohols also contain 2 electron pairs. Amines has 1 electron pair. Hydroxide ion has 6 electron pairs, and that's why you end up with a minus 4 mole charge. Alkoxide ion, similar to hydroxide, you have 6 electrons. You have a minus charge on the oxygen. Amide, with a minus here, you have a negative charge on the nitrogen. And then the last one is what we call enolates. If the alpha position loses a proton, you end up with a minus charge on that carbon, the alpha carbon, which can then be delocalized into the structure. So you get a minus charge going back there to form a double bond. Then at the same time you break the other double bond, the electrons flow to oxygen, and you end up with 6 electrons around oxygen with a 4 mole negative charge. So that shows that this structure here is stabilized by resonance. Lewis acids, they are electron pair acceptors, while Lewis bases are electron pair donors. We focus on electron pairs when we're dealing with Lewis definition of acids and bases. Lewis acids have a positive charge, or they have empty orbitals that can be occupied by electrons. Example of that would be compounds of boron and aluminum. That's group 3A. Aluminum and boron compounds. For example, if you have something like BH3, the Lewis structure for that, you will see that you only have a total of 6 electrons. That means boron has what we call a hole, and therefore it has room for electron pairs from a Lewis base. And then the last type of Lewis acid are transition metal salts. And that's because transition metals can form what we call expanded octet. So they can have more than 8 electrons on their outer energy shell.